You hear interstellar visitor and you think close call, asteroid movies, Earth in danger. But 3I Atlas does something nobody talks about. It screams past Mars at 18 million miles, swings by Venus at 60 million, comes within 33 million miles of Jupiter. And Earth? Not even close. 167 million miles, 269 million kilometers, almost twice the distance between Earth and the Sun. The math doesn't add up by accident. The trajectory is tilted 175 degrees to the ecliptic. That's 5 degrees off the planetary plane, moving retrograde backward through the solar system. Every planet it visits on purpose. Earth, it dodges. Not a near miss, a calculated skip. Atlas, survey telescope in Chile, spots a faint magnitude 18 object crawling through Sagittarius. Temporary designation A11PL3Z, 4.5 AU from the Sun, just inside Jupiter's orbit, moving at 61 kilometers per second, 140,000 miles per hour. Twice Earth's orbital speed. Within hours, follow-up observations from the Zwicky Transient Facility confirm what the math already screamed: hyperbolic trajectory. Eccentricity 6.14. Not bound to the Sun, never coming back. The Minor Planet Center lists it on the Near-Earth Object Confirmation page. Initial calculations suggest it might come close to Earth's orbit. 24 hours later, refined data kills that theory. The object won't come near Earth, it's interstellar. Third confirmed visitor from beyond our solar system. First was 1I Oumuamua in October 2017. Second was 2I Borisov in August 2019. Now 3I Atlas. The I stands for interstellar. If you value documented interstellar physics and comet chemistry like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory Small Body Database computed by D. Farnakia at Epic, JD 2,460,868.5, the James Webb Space Telescope. NIRSPEC campaign results published in ArXiv preprint 2508.18209 by Martin Cordner and team from NASA Goddard on August 26, 2025. And the Gran Telescopio Canarias Osiris spectroscopy paper ArXiv 2507.12922, published July 25, 2025 by De La Fuente Marcos. These aren't press releases. These are raw observation logs, orbital mechanics, computations, and infrared spectroscopy data from the largest optical telescope in the world. Now back to the information. Not the thin disk where the Sun lives. The thick disk is older, 7 billion years minimum, maybe 14 billion. Twice the age of Earth, 3 times older than life on this planet. Matthew Hopkins at Oxford ran the kinematics backward, traced the comet's galactic orbit. Its vertical velocity component, 18.5 kilometers per second above the galactic plane, puts it in thick disk population. That's not speculation, that's orbital mechanics. When you move that fast perpendicular to the galactic plane, you don't belong to the young thin disk, you're ancient. You predate the Sun. Hopkins published this July 11th, 2025, at the Royal Astronomical Society National Astronomy meeting in Durham. Confidence interval, 68%. 2/3 chance this comet is older than the solar system. 9 to 13 billion years ago when star formation in the Milky Way peaked. Metal, poor stars. Low in heavy elements compared to the Sun. If 3I Atlas formed around one of those stars, its chemistry should show it. Early predictions said water-rich, high water mass fraction. That would make sense for a comet from a cold protoplanetary disk around an ancient star. August 6th, 2025, James Webb Space Telescope turns NIRSPEC toward 3I Atlas, 3.32 AU from the Sun. Infrared spectroscopy spanning 0.6 to 5.3 micrometers. The coma lights up, carbon dioxide dominated. CO 2 to H2O, mixing ratio 8:1, among the highest ever observed in any comet. 6.1 sigma above the trend for long period in Jupiter family comets. Only one outlier comes close, C 2016 R2, and even that's different. 3. I Atlas isn't just carbon dioxide rich, it's structurally bizarre. Dust rich in amorphous carbon, olivine, pyroxene, crystalline silicates, polycyclic aromatic hydrocarbons strongly suggested in the 3 to 8 micrometer residuals. But the CO2 dominates. Why? 2 theories. Formation near the CO2 ice line in its parent protoplanetary disk, where temperatures favor carbon dioxide condensation over water. Or prolonged exposure to high ultraviolet radiation in interstellar space before arrival, altering surface chemistry and creating an insulating crust that traps water below while CO2 sublimates freely. Either way, the composition doesn't match solar system comets. This is chemically alien material. The coma expanded 60% in 2 weeks at 6.4 AU from the Sun. That distance is beyond Jupiter. Most comets don't activate that far out. Water ice sublimates weakly at those temperatures. But carbon dioxide and carbon monoxide? They sublimate aggressively. NASA's Transiting Exoplanet Survey Satellite observed the comet from May 7th to June 3rd, 2025. Already bright and active at 6.4 AU. Dust mass loss rate between 12 and 120 kilograms per second. By July 21st, Hubble Space Telescope imaged the coma in high resolution. Teardrop shaped. Nucleus diameter constrained between 440 meters and 5.6 kilometers. Most likely, estimate under 1 kilometer. Small but hyperactive. Something strange happens when you look at the tail. Bryce Bolin at Palomar Observatory and the Rubin team both noted it. The tail points toward the sun, not away. Normally, radiation pressure pushes dust anti-solar. The tail streams backward. 3I Atlas, dust elongates sunward. Explanation. Massive particles ejected forward by outgassing, too heavy for radiation pressure to reverse at that heliocentric distance. They continue their forward momentum briefly before solar gravity and radiation catch up. The Very Large Telescope observed this on September 7th, 2025, using spectroscopy. Hydrogen cyanide production rate, 1.5 times 10 to the 25th molecules per second. Atomic nickel detected, CN emission lines confirmed. Nickel to CN ratio orders of magnitude higher than typical comets. The comet's rotating. Period, 16.79 hours plus or minus 0.23 hours. From photometric analysis by De La Fuente Marcos using the 10.4 meter Gran Telescopio Canarias. Rotation state determined from light curve modulation across 60 observational epochs. Hyperbolic excess velocity 58 kilometers per second. That's the speed it had at infinite distance from the Sun before gravity accelerated it inward. Fastest of all 3 known interstellar objects. Oumuamua, 26 km per second. Borisov, 32. 3I Atlas, 58. Moving through the Milky Way for millions or billions of years, accumulating velocity from gravitational interactions with stars and molecular clouds. When it entered the solar system, it was already moving too fast to be captured. Eccentricity, 6.14. Anything above 1 is hyperbolic. Unbound. This object will escape back to interstellar space and never return. Most solar system objects orbit in the same direction as the planets, prograde, within a few degrees of the ecliptic. 3I Atlas moves backward and slightly below, coincidentally close to the planetary plane but opposite direction. Avi Loeb at Harvard calculated the probability. Alignment within 5 degrees, 0.2%. Fine-tuning of arrival times at planetary orbital radii, 0.02%. Combined probability, less than 1 in a million. He published this October 8th, 2025. His conclusion, either extremely unlikely natural coincidence or design trajectory. Most astronomers lean natural. The ecliptic alignment is unusual but not impossible. The thick disk origin provides billions of years for velocity changes via stellar encounters. Still, the geometry is striking. October 3rd, 2025, 3I Atlas passes Mars. Distance, 0.19 AU, 28 million kilometers, 18 million miles. ESA's Mars Express and ExoMars Trace Gas Orbiter image. The comet using color and stereo surface imaging system. CASA's principal investigator Nick Thomas. The comet is around 10,000 to 100,000 times fainter than our usual target. 5-second exposures. Mars is the closest planetary encounter 3I Atlas experiences. NASA's Perseverance rover attempts to image the comet from Jezero crater, latitude 18 degrees north. The comet tracks high in the northern Martian sky because of Mars's orbital inclination relative to 3I's trajectory. 1.36 AU from the Sun, 203 million kilometers, 126 million miles, between the orbits of Earth and Mars. Maximum speed, 68 kilometers per second relative to the Sun. Solar elongation at perihelion, 2.59 degrees as seen from Earth. The comet sits behind the Sun from Earth's perspective. Unobservable from ground-based telescopes. Hubble can't point there, Webb can't point there. Too close to solar glare. The timing ensures Earth-based observers miss the peak, but spacecraft at Mars saw it approach. And spacecraft beyond Mars will see it leave. The spacecraft is en route to Jupiter, but positioned 0.43 AU from the comet on November 4th. 64 million kilometers, 5 times closer than Earth at that moment. JUICE operates Janus Visible Imager, Magis Infrared Spectrometer, SWI submillimeter wave instrument. Post-perihelion observations at phase angles impossible from Earth. Coma brightens, outgassing increases, dust production peaks. JUICE captures it all. 167 million miles. Safe, no threat. The comet emerges from behind the sun in mid-November, pre-dawn sky. Magnitude 12. Requires 8-inch telescope minimum, moves through Virgo into Leo by year-end, fades as heliocentric distance increases. Ground-based campaigns from Keck, Very Large Telescope. Gemini obtain high-resolution spectra. Sulfur to oxygen ratios. Isotopic composition. Carbon-12 to carbon-13 ratio measured, similar to Earth, formed in environment with comparable carbon processing. But the CO2 dominance remains unexplained by solar system formation models. Distance from comet, 53.6 million kilometers at closest. UVS ultraviolet spectrograph. GIRM infrared auroral mapper. MWR microwave radiometer. Multi-wavelength characterization of nucleus size, albedo, thermal emission, rotation state, coma morphology. Jupiter's gravity perturbs the trajectory slightly, but the comet remains hyperbolic. After Jupiter encounter, 3I Atlas leaves the inner solar system. No more planetary flybys. Trajectory carries it out toward interstellar space at roughly the same hyperbolic excess velocity it entered with, 58 kilometers per second. In a few thousand years, it will be farther from the sun than Oumuamua is now. In a million years, it will be dozens of light years away, drifting through the thick disk, maybe encountering another star system, maybe not. 3. Atlas visits planets but avoids Earth deliberately? No, physics explains it. The orbital plane alignment is 5 degrees off the ecliptic. The perihelion distance is 1.36 AU. Earth orbits at 1 AU. Mars orbits at 1.52 AU. 3I's perihelion sits between them. But Earth's orbit is circular. Mars' orbit is elliptical. When 3I reaches perihelion, Earth is on the wrong side of its orbit, not in the path. The comet passes through the inner system retrograde. It crosses the ecliptic twice per orbit, but those crossings occur at distances where no planets are present at that time. Mars is close because Mars's orbit is eccentric, and its position in October 2025 places it near the intersection. Venus is close after perihelion because the comet's outbound trajectory crosses Venus's orbital radius in November. Earth, the geometry never allows close approach. Minimum distance 1.8 AU in December occurs after the comet is outbound, and Earth is positioned on the opposite side of the Sun, from the comet's ascending node. Jupiter's close approach in March 2026 happens because the comet's trajectory passes through Jupiter's orbital radius 6 months after perihelion. Jupiter's 12-year orbit means its position is predictable. The comet arrives at the right place at the right time by orbital mechanics, not design. But the math is elegant. Hyperbolic trajectory with eccentricity. 6.14 means the path is nearly straight at large distances. Comes in fast, bends around the sun, leaves fast. The 5-degree inclination keeps it near the ecliptic long term. Gravitational perturbations from planets are minimal because encounters are too distant and too fast. Jupiter at 0.36 AU imparts velocity change on the order of meters per second. Negligible compared to 58 kilometers per second hyperbolic excess. The trajectory is ballistic, set billions of years ago by ejection from its parent star system. Modified slightly by stellar encounters in the thick disk, arrives at the solar system with the velocity and angle it has. The planets happen to be where they are. The comet doesn't care. Jupiter family comets average 0.5 to 1.5. Main belt comets and centaurs fall in similar ranges. C 2016, R2 is the only outlier with CO2 to water above 5. That comet's origin is debated. 3I Atlas at 8 to 1 stands alone. The James Webb data, published August 26, 2025 by Cordner, shows the mixing ratio is 6.1 standard deviations above the trend as a function of heliocentric distance. Not an outlier, an alien data point. In a protoplanetary disk, water ice condenses at roughly 150 Kelvin. Carbon dioxide ice condenses at roughly 65 Kelvin. If 3I Atlas formed in a region where temperatures hovered near 65 Kelvin, CO2 would dominate the ice composition. Water would be present, but secondary. This requires the comet formed far from its parent star in a cold outer disk, possible for thick disk stars with different metallicity and disk structure than the Sun. Second scenario, irradiation. Interstellar space is not empty, cosmic rays. UV photons from distant stars. Radiation processes the surface. Water ice photodissociates more easily than CO2 ice. Over billions of years, a surface crust forms, depleted in water. enriched in refractory organics and carbon dioxide. When the comet approaches the sun, the crust insulates the interior. CO2 sublimates preferentially because it's more volatile and closer to the surface. Water remains trapped below. Observations support this. The water ice signature detected at 2 micrometers by Gemini South on July 5th at NASA Infrared Telescope Facility on July 14th suggests subsurface water. But the coma shows little water vapor until later in the trajectory. Neil Gehrels Swift Observatory detected OH emission from water photolysis July 31st to August 1st. Production rate 1.3, 6 times 10 to the 27th molecules per second. That's not negligible, but CO2 production is 8 times higher. The dust composition also stands out: 25% amorphous carbon, 19% amorphous magnesium iron olivine, 16% amorphous pyroxene, 39% crystalline olivine, crystalline mass fraction 0.384. Typical solar system comets have crystalline fractions around 0.2 to 0.3. 3I Atlas is more crystalline. That implies thermal processing, either in the parent protoplanetary disk or during formation. Polycyclic aromatic hydrocarbons detected in the 3 to 8 micrometer spectrum. PAHs form in carbon-rich environments. Thick disk stars are metal-poor, but not carbon-poor. If the parent star had subsolar iron abundance but near solar carbon, PAH formation in the disk would be enhanced. The dust tells the story of where this comet was born. Input: vertical velocity component, radial velocity, transverse velocity. Output: probability distribution over galactic populations. 3, I Atlas has U equals negative 51 km per second away from galactic center, W equals positive 18.5 km per second above galactic plane. The W velocity is high. Thin disk stars have W dispersion around 22 km per second. Thick disk stars have W dispersion around 40 km per second. 3I sits between, but leans thick disk. Age range: 7.6 to 14 billion years with 68% confidence. The solar system is 4.56 billion years old. Earth is 4.54 billion. If 3I Atlas is even 7 billion years old, it predates Earth by 2.5 billion years. If 14 billion, it formed when the universe was less than 1 billion years old. Not impossible. First stars formed a few hundred million years after the Big Bang. Thick disk stars formed 1 to 4 billion years later. 3I could be a relic of the galaxy's youth. The Gaia Space Observatory mapped 1 billion stars, with precise astrometry over 12 years. GUO identified 93 nominal encounters with stars within 10 million years, 62 significant encounters. None produced meaningful perturbation. Every encounter too fast or too distant to change the orbit. The comet has been traveling essentially ballistic for at least 10 million years, probably longer. Trace it back 100 million AU, and you find no parent star. The object has been wandering interstellar space for cosmological timescales. It could have been ejected from its parent system billions of years ago when that star was young. Gravitational scattering by a giant planet. Close encounter with a stellar companion. Passage through a dense star cluster. Once ejected, it drifted through the Milky Way. Thick disk orbits take stars and their debris vertically through the galactic plane. 3I rides that vertical motion. Eventually, by sheer probability, it intersects the solar system. We see it once, it leaves, never comes back. The sunward tail is still weird. Bullen's observations from Palomar show elongation toward the sun in early images. Typical comets show antisolar tails. Dust pushed by radiation pressure, ion tails shaped by solar wind. 3I shows neither clearly. Explanation: large particles. Millimeter scale grains, ejected by gas drag during outgassing. Too massive for radiation pressure to reverse their motion immediately. They continue forward briefly. Solar gravity eventually pulls them back, but the effect creates apparent sunward elongation in early observations. By September, the tail morphology changes. Hubble images show more typical coma shape, teardrop pointed away from the sun. The early sunward tail was transient, artifact of large particle ejection at high heliocentric distances, where radiation pressure is weak. Not anomalous, just unusual. The polarization is anomalous. Stefano Bagnullo and team observed 3I using FORS-2 at the Very Large Telescope, ALPHOSC at Nordic Optical Telescope, FORIRO-2 at Rosen Observatory, July 17th to August 28th. Phase angle range 7.7 to 22.4 degrees. Heliocentric distance 3.9 to 2.6 AU. R-band polarimetry. The comet shows extreme negative polarization. Minimum P equals negative 2.7% at phase angle 7 degrees. Inversion angle 17.1 degrees. Typical comets, inversion angle 20 to 22 degrees. 2. I Borisov, 20.5 degrees. 3. I Atlas, 17.1. The negative branch is deeper and shifted to smaller phase angles than any known comet class. The slope at inversion is steep. This implies unusual dust properties, submicron grains with high refractive index, or non-spherical particles with specific size distributions. The polarization published September 11, 2025 in ARXIV 2509.05181 by Bagnullo confirms. The dust is not like solar system comet dust. Different formation environment, different composition, different structure. 22.8% per micrometer in the optical range, 400 to 700 nanometers, measured by Southern African Large Telescope and Nordic Optical Telescope. Published in Spectroscopy Journal, September 2025. Reddening indicates organic-rich surface, tholins. Complex hydrocarbons formed by irradiation of ices. Red color is common in outer solar system objects, Kuiper Belt, centaurs. But 3 eyes reddening is consistent with interstellar irradiation. Billions of years in the radiation field of the galaxy produce similar spectral slopes. The comet looks red because it's old and processed. Upper limit on CN column density. By September 7th, James Clerk Maxwell Telescope detected hydrogen cyanide, HCN production rate 1.5 times 10 to the 25th molecules per second. That's late activation. HCN is a common cometary volatile. It sublimates around 200 Kelvin. At 2.3 AU in September, temperatures reached that threshold. CN is a photolysis product of HCN. The delayed CN emission supports the insulating crust hypothesis. Volatiles are trapped below a processed surface layer. As heliocentric distance decreases and temperature increases, the crust fractures. Subsurface ices escape. Activity ramps up. Nickel in comets is rare, detected in a few solar system comets, but always trace amounts. 3. I Atlas shows prominent nickel lines. Source: dust grains, forsterite and iron nickel metal grains heated by solar radiation. Nickel sublimates at temperatures around 1,300 Kelvin. Surface grains reaching that temperature release nickel atoms. The high nickel abundance implies metal-rich dust. Thick disk stars are metal poor in iron and heavy elements. But dust in their protoplanetary disks can still contain refractory metals if the disk accreted material from earlier stellar generations. Nickel emission doesn't prove alien origin. It proves unusual dust composition consistent with thick disk formation. Carbon-12 to carbon-13 ratio, terrestrial, measured from CO, 2 lines, and JWST NIR spec data. Ratio close to Earth's 90 to 1. That means the carbon isotopes in 3 I's parent protoplanetary disk had similar nucleosynthetic history as the Sun's disk. Heavy elements synthesized in stars, ejected in supernovae, incorporated into new generations of star-forming clouds. The isotope ratio convergences across the galaxy over billions of years. 3 I formed from material that underwent comparable stellar processing. Not chemically alien in isotopes, chemically alien in volatiles. 3 I's water formed cold, consistent with outer disk formation near the CO2 ice line. The water we detect now was ice for billions of years, never heated above a few tens of Kelvin until entering the inner solar system. When it sublimates, it carries the memory of its formation temperature in the spin statistics. The ratio is a thermometer pointing at the ancient cold. Dust follows. H2O emission weaker, more distributed. The asymmetry is typical for comets with discrete active regions. Localized jets. The nucleus rotates 16.79 hours. As different areas face the sun, activity varies, but the sunward enhancement is strong. Suggests the insulating crust is thinner on the sunward hemisphere, or fractures more easily under thermal stress. Not all surfaces are equal. Some retain primordial ice, some are processed and sealed. 8 documented anomalies: ecliptic alignment, sunward tail, large mass, planetary flyby trajectory, nickel-enriched coma, low water content, extreme negative polarization, arrival direction within 9 degrees of the 1977 WOW signal. He assigns lobe scale rank 4. Unusual but not conclusive, calls for systematic follow-up. Most astronomers disagree. Tom Statler at NASA: it looks like a comet. It does comet things. Every anomaly has natural explanations. Thick disk origin explains chemistry. Hyperbolic trajectory explains speed. Random interstellar arrival explains ecliptic alignment as low probability but possible. The WOW signal coincidence is coincidence. No SETI signals detected from 3I, no radio emissions, no optical beacons, no course corrections. The comet follows Newtonian gravity. Nothing about its trajectory requires intelligence, But the debate continues. Papers argue both sides. Data accumulates. We're covering the most fascinating intersection of chemistry, orbital mechanics, and galactic archaeology. This is the second time we're asking because this is important. Comment from which city you're hearing this from. This script uses data from NASA JPL Horizons, ephemerides updated in real time, ArcSev preprint 2508.15768 by Eubanks on spacecraft observations, and Astronomy and Astrophysics journal publication by Bagnulo on polarimetry. These are peer-reviewed sources and orbital solutions computed from 762 observations over 60-day time spans. Back to the information. Epoch JD 2,460,868.5. Barycentric dynamical time, July 12th, 2025. J 2000.0, ecliptic and equinox, 762 observations. Observational time span 60 days. Solution date, July 21st, 2025. The orbit is constrained to sub-kilometer precision at perihelion. Eccentricity uncertainty, plus or minus 0.0006. Perihelion time uncertainty, plus or minus 1 minute. This is not guesswork. This is the most precisely determined interstellar object trajectory ever computed. The orbit will not change. The comet will not hit anything. It will pass where the math says it will pass. Gas composition, outgassing rates. Monitor through December as the comet recedes. JWST observes again in December, post-perihelion. Track composition changes. Temperature-dependent sublimation, surface evolution. Ground-based telescopes from Keck, VLT, Gemini, Magellan obtain high-resolution spectra through early 2026. Isotope ratios, molecular abundances, rotation state, nucleus size refined. Spacecraft observations from JUICE in November provide post-perihelion coma morphology at phase angles unavailable from Earth. Juno observations in March characterize the nucleus at Jupiter distance, thermal emission, albedo, shape. Every instrument adds a data point. Every observation refines the model. The comet's high CO2, moderate water, crystalline silicates, PAH content fits that profile. If the comet spent billions of years in interstellar space, cosmic ray irradiation would process the surface, amorphize silicates near the surface, polymerize organics, create a radiation crust. The observed surface properties fit. If the comet was ejected from its parent system early, before the star's protoplanetary disk fully dissipated, it could have accreted additional ices during ejection. Gravitational scattering sends the comet outward through the disk. It sweeps up volatiles on the way out, ends up CO2 rich if it passed through the outer disk cold traps. Metallicity increasing. 3, I would be a fossil from that era. 14 billion years old means formation within a billion years of the Big Bang. First stars, population 2 stars, near zero metallicity. The comet chemistry doesn't fit that extreme. Iron and magnesium in the dust imply some metal enrichment. Probably not first generation, probably second or third generation stars. Age 7 to 10 billion years is most consistent. Cosmic noon, peak star formation, thick disk assembly. The comet is a relic of the galaxy's most productive era. The trajectory through the solar system is a straight line probe. Comes in from infinity, passes through, leaves to infinity. No capture, no orbit, one shot. The closest we'll get to sending a probe to the thick disk is studying this comet while it's here. We can't reach thick disk stars. They're thousands of light years away, but one of their comets reached us, delivered itself. We point telescopes, we collect photons, we decode the chemistry, we read the isotopes, we reconstruct the formation environment. It's interstellar archaeology. The comet is the artifact. The data is the excavation. 3, I entered the solar system with specific position and velocity. Earth orbits with specific period and phase. They don't intersect. Mars was close because Mars was at aphelion near 3 I's descending node. Venus was close because Venus orbits fast and crosses 3 I's outbound path in November. Jupiter was close because 6 months after perihelion, the comet reaches Jupiter's orbital radius, and Jupiter is there. Geometry, not luck, not design, physics. 3, I was ejected from its parent system eons ago. It wandered through the thick disk. Stellar encounters nudged it. Molecular clouds perturbed it. The galactic potential shaped its orbit. Eventually, the orbit intersected the sun's trajectory through the galaxy. The sun moves at 220 kilometers per second around the galactic center. 3, I moves at roughly 170 kilometers per second in a different direction. Relative velocity at infinity, 58 kilometers per second. The encounter was inevitable once their galactic orbits crossed. But the crossing took billions of years to happen. The comet has been traveling longer than Earth has existed. It finally arrives. We get one look. It leaves. And Earth can't see it. Solar elongation 2.59 degrees. The sun is in the way. Hubble can't observe within 5 degrees of the sun. JWST can't observe within 50 degrees. Ground-based telescopes are blinded by daylight. The only observers are Mars orbiters and spacecraft beyond Mars. ESA's Mars Express and ExoMars Trace Gas Orbiter watch the approach. NASA's Psyche watched from 0.3 AU in September. JUICE watches in November. The peak happens in darkness from Earth's view. By the time the comet emerges in mid-November, perihelion is past. Activity declining. Coma shrinking. The show is over. JWST pre-perihelion data establishes baseline. Post-perihelion observations track evolution. Did water production increase? Did dust properties change? Did the coma expand or contract? Did new volatiles activate? Comparing pre- and post-perihelion data reveals how the comet responded to peak solar heating. That response encodes surface structure, crust thickness, ice distribution, thermal conductivity. Every measurement constrains the model. Hubble constrains upper limit 5.6 kilometers, lower limit 440 meters, most likely under 1 kilometer. But the coma is large, 15,000 kilometers diameter in July at 4 AU, 26,000 by August at 3 AU. The coma to nucleus ratio is extreme. Small nucleus, huge coma, high activity. Dust production rate 120 kilograms per second at 6 AU. For a 1 kilometer nucleus, that's stripping thousands of tons per day. The nucleus can't sustain that rate indefinitely. Either the surface area is larger than estimated, or the activity is localized to discrete jets. Probably both. Hubble and JWST images show asymmetric coma. Jets from active regions. Rotation modulates the jets. The 16.79-hour period cycles, the activity on and off as different regions face the sun. Above 700 Kelvin, then cool and preserve the crystalline structure. Where did 3 eyes silicates crystallize? In the inner protoplanetary disk of its parent star, close to the star where temperatures are high, then transported outward. Mixed into the cold outer disk where the comet formed. That process, radial mixing in protoplanetary disks, is standard. But it requires a disk that was active long enough to mix hot inner material into the cold outer regions. Thick disk stars are old. Their disks existed billions of years ago. We can't observe them directly, but we can infer disk structure from the comets they produced. 3, I tells us, thick disk protoplanetary disks had radial mixing. They processed material thermally. They delivered crystalline silicates to the comet-forming regions. The PAH detection is tentative but intriguing. Polycyclic aromatic hydrocarbons are large carbon molecules. Benzene rings fuse together. They form in carbon-rich gas phase environments. Stellar winds from carbon stars. Outflows from dying stars. Shock processing in molecular clouds. PAHs are ubiquitous in the interstellar medium, but detecting them in a comet coma means they survived billions of years frozen in the nucleus, now sublimating into the coma. The 3 to 8 micrometer spectrum shows excess emission consistent with PAH vibrational bands. Not definitive. Needs confirmation. If real, it means 3, I carried complex organics from its parent star system. Those organics are now released in the coma. Some will be ionized by solar UV. Some will condense back onto dust. Some will escape to interstellar space. The coma is a laboratory for organic chemistry. Every molecule detected adds to the inventory of interstellar organic compounds. Direction, roughly opposite to where it came from. The encounter with the sun bent the trajectory, but didn't change the hyperbolic nature. The comet leaves faster than it arrived because it gained kinetic energy falling into the sun's gravity well and converted that energy back to velocity climbing out. But the net change is small. The comet is still unbound, still moving too fast to stay. In 10 years, it will be farther from the sun than Neptune. In 100 years, farther than the Kuiper Belt. In 1,000 years, halfway to the Oort cloud edge. In 10,000 years, in the Oort cloud proper. In 100,000 years, interstellar space again. It will drift through the thick disk, maybe encounter another star, maybe get perturbed, maybe continue drifting. We'll never know. We saw it once. That's enough. 10 million years. 93 stellar encounters. None significant. Trace back 100 million years. Still no parent star. The comet has been wandering for cosmological timescales, billions of years, aimless, until it intersected us. The trajectory we measured is not the product of recent events. It's the cumulative result of billions of years of galactic dynamics. Every stellar encounter shifted the velocity by meters per second. Every passage through a molecular cloud added perturbations. Every orbit around the galactic center changed the inclination slightly. The trajectory is a fossil. Encoded in the orbital elements is the entire history of the comet's journey through the Milky Way. We can't decode all of it. We don't have enough data, but we know it's there. 3I Atlas is a messenger from the deep galactic past. The message is in the chemistry and the orbit. We're reading it now. Different stellar populations. The comet was ejected from its parent system billions of years ago. It wandered through the thick disk while the thin disk was still forming, while the sun was still condensing from a molecular cloud, while Earth was still molten. The comet was already frozen, already traveling. It drifted for eons, finally arrived at the solar system. The timing is random, the geometry is random, but the physics is deterministic. Once the comet entered the solar system with its velocity and trajectory, the outcome was fixed. Mars at 18 million miles, Earth at 167 million, Jupiter at 33 million. Those numbers were set by orbital mechanics, computed billions of years ago by gravity and motion. We just watched it happen. We measured it, we decoded it, we learned. The comet didn't care, the orbit didn't care, physics doesn't care, but we do. Because for a few months in 2025, we had a visitor from the deep galactic past, a 7 billion-year-old relic, a time capsule from cosmic noon, a fragment of a dead star's protoplanetary disk. We pointed every telescope we had. We captured every photon we could. We extracted every data point. The comet is gone now, moving outward, fading. The data remains, the chemistry remains, the story remains. 3I Atlas told us where it came from, told us how old it is, told us what it's made of, told us the thick disk produces carbon dioxide-rich comets with crystalline silicates and PAHs and extreme polarization and sunward tails and nickel vapor and delayed water activation. Told us interstellar space is full of these objects. Told us the galaxy is ancient and complex and we're just beginning to sample it. One comet at a time, one trajectory at a time, one data set at a time. The orbit missed Earth. That's not the story. The story is we caught it anyway.